Let us begin slowly at the beginning. Abstract algebra is a subject about structure. At first, this may sound a little distant from the algebra we learned earlier. Earlier algebra often feels like a language of numbers, expressions, and solving for unknown quantities. We learn how to move terms from one side to another. We learn how to expand, factor, simplify, and compute. We become familiar with numbers, variables, and formulas. But abstract algebra asks us to pause and look beneath these familiar activities. It asks, what are the rules that make these calculations possible? It asks, what does it mean to combine two things? It asks, when can we undo an action? It asks, when are two mathematical worlds really the same, even if they look different? And, very importantly, it asks, what kind of structure is created by an operation? This is the quite central idea of abstract algebra. We are not merely interested in individual numbers. We are interested in systems. We are interested in collections of objects together with rules for combining them. The objects might be numbers, but they do not have to be. They might be rotations of a shape. They might be symmetries of a polygon. They might be permutations of a finite set. They might be transformations of space. They might be classes of remainders after division. They might even be functions. Abstract algebra gives us a language for seeing the same pattern in many different places. Let us pause and reflect on this. When we add integers, we are combining two integers to obtain another integer. When we rotate a square and then rotate it again, we are combining two movements to obtain a new movement. When we permute a list of objects and then permute it again, we are combining two rearrangements to obtain another rearrangement. These examples look different on the surface. One involves numbers. One involves geometry. One involves arrangements. But in each case, there is a collection of things, and there is a rule for combining two things. This is where abstract algebra begins. It begins not with formulas, but with operations. A great deal of abstract algebra is the careful study of operations. We ask whether an operation is well behaved. We ask whether it has an identity element, something that does nothing. We ask whether every element can be undone by another element. We ask whether the order in which we group repeated operations matters. We ask whether a smaller system lies inside a larger system. We ask whether one structure can be transformed into another structure while preserving the operation. These questions are simple to state, but they lead very far. They lead to group theory, ring theory, field theory, modules, representation theory, Galois theory, and many other areas. But tonight, or in this gentle lecture, we remain close to the foundations. We focus on groups, operations, and symmetry. A group is one of the central objects of abstract algebra. It is a mathematical structure in which elements can be combined. The combination behaves associatively. There is an element that does nothing, and every element can be undone. This is the formal idea, but for now let us keep the intuition in mind. A group is a world of reversible actions. That phrase is worth repeating. A group is a world of reversible actions. If you do something, you can undo it. If you rotate a shape, you can rotate it back. If you move along a number line, you can move back. If you rearrange objects, you can rearrange them back. Groups are the natural language of symmetry because symmetries are reversible transformations. A symmetry of an object is a way of moving or transforming it so that, after the transformation, it still looks the same in the relevant sense. A square can be rotated and reflected in ways that preserve its shape. A triangle has its own symmetries. A circle has many more. A polynomial may have hidden symmetries among its roots. A number system may have symmetries in its arithmetic. Abstract algebra allows us to speak about all of these in one language. So the first major lesson is this: abstraction is not meant to make mathematics vague. It is meant to make repeated patterns visible. Instead of studying addition here, rotations there, and permutations somewhere else, we study the common structure that they share. Let us now move toward the basic ingredients. The first ingredient is a collection of objects. The second ingredient is a rule for combining two objects from that collection. Such a rule is called a binary operation. The word binary here simply means that the operation takes two inputs. It takes one element and another element, and it produces an output. The output is meant to be another element of the same world, at least when the operation is closed. Closure is the property that combining two elements of the collection never takes us outside the collection. If we are working with integers and we add two integers, we remain among the integers. If we are working with rotations of a square that preserve the square, and we perform one such rotation after another, we still have a rotation that preserves the square. If we are working with permutations of three objects, and we do one permutation after another, we still have a permutation of those three objects. Closure says that the operation belongs to the world we are studying. It does not escape. This is a quiet but important condition. Without closure, the collection and the operation do not form a self-contained algebraic system. We would combine elements and suddenly find ourselves outside the universe we intended to study. So closure is the first sign that we have a stable algebraic setting. The next property is associativity. Associativity concerns repeated operation. Suppose we want to combine three elements. We can first combine the first two, and then combine the result with the third. Or we can first combine the last two, and then combine the first with that result. Associativity says that these two procedures lead to the same final result. This is not the same as saying that order does not matter. That is a different property. Associativity is about grouping, not ordering. It is worth repeating this distinction gently. Associativity does not say that we may swap the order of two elements. It says that when the order is fixed, the placement of parentheses, or the grouping of the operation, does not affect the result. In many familiar systems, associativity feels natural. Adding whole numbers is associative. Multiplying numbers is associative. Composing transformations is associative. If we do one transformation, then another, the final transformation does not depend on how we mentally group the first two or the last two. The sequence of actions is what matters. Associativity is one of the most important technical conditions in algebra because it lets us combine long strings of elements without constantly worrying about how they are grouped. It gives stability to repeated combination. Now we come to identity element. An identity element is an element that leaves every other element unchanged when combined with it. It is the algebraic version of doing nothing. For addition, the identity is the number that adds nothing. For multiplication, the identity is the number that scales nothing. For rotations, the identity symmetry is the rotation that leaves the object exactly as it was. For permutations, the identity permutation is the rearrangement that does not rearrange anything. The identity element may seem humble, but it is essential. It gives us a reference point. It tells us what it means to do no action. In a system of transformations, the identity is the transformation of standing still. In a system of numbers, it is the element that has no effect under the operation. Let us pause and reflect. An operation tells us how to combine. Closure says the result remains inside. Associativity says repeated combination is stable. An identity element says there is a neutral action, a way to combine without changing anything. Then comes the idea of inverse elements. An inverse element is an element that undoes another element. If we combine an element with its inverse, we return to the identity. In the language of actions, the inverse is the reverse action. If a rotation turns a shape clockwise, its inverse turns it back. If a translation moves something forward, its inverse moves it backward. If a permutation rearranges objects, its inverse returns them to their original places. Inverses are the algebraic expression of reversibility. This is why groups are so deeply connected to symmetry. Symmetries are not merely operations. They are reversible operations. If a movement preserves the structure of an object, then undoing that movement also preserves the structure. Symmetry lies naturally in a group because every symmetry can be reversed. Now we can describe a gradual hierarchy of algebraic structures. The first structure we mention is a semigroup. A semigroup is a collection with an associative binary operation. That is all. There is a set of elements. There is a way to combine two elements. The operation is closed. The operation is associative. But there may be no identity element, and elements may not have inverses. A semigroup is already meaningful because associativity alone is powerful. It allows repeated products or repeated combinations to be discussed coherently. Many processes that can be repeated naturally form semigroups, even when they cannot necessarily be undone. Then we add an identity element. A semigroup with an identity element is called a monoid. A monoid is a little richer. It has all the structure of a semigroup, and it also has a neutral element. There is an element that does nothing. This allows us to speak of zero repetitions of an operation, or of an empty combination, in a natural way. Examples of monoids appear everywhere. Strings under concatenation form a monoid, where the empty string is the identity. Functions from a set to itself form a monoid under composition, where the identity function does nothing. Non-negative integers under addition form a monoid, where the number that represents adding nothing is the identity. But in a monoid, not every element must be reversible. To reach groups, we require inverses. A group is a monoid in which every element has an inverse. Or, said more slowly, a group is a collection of elements with a rule for combining them, where the combination stays inside the collection, where repeated combination is associative, where there is an identity element, and where every element can be undone by another element in the collection. It is worth repeating in a slightly different way. A group is an algebraic system of reversible operations. This is often the most intuitive way to remember it. When you hear the word group, think first of symmetry, motion, transformation, and reversibility. Think of actions that can be performed one after another with a neutral action and with an undoing action for each one. Now let us move more deeply into the idea of groups as the mathematics of symmetry. Imagine a square lying flat on a table. You may rotate it by a quarter turn, or by a half turn, or by 3/4 turns, or by a full turn that brings it back to where it started. You may also reflect across certain axes. Some reflections flip it across vertical or horizontal lines. Others flip it across diagonal lines. After each of these movements, the square still occupies the same overall position. Its corners may have moved, but the square as a shape appears unchanged. Each such movement is a symmetry of the square. Now suppose you perform one symmetry and then another. For example, you may rotate the square and then reflect it. The result is again a symmetry of the square. So symmetries can be combined. The rule for combining them is simply do one, then do the other. This combination is associative because composing actions is associative. There is an identity symmetry, namely doing nothing. Every symmetry has an inverse because every motion can be undone. A rotation can be reversed by rotating back. A reflection is often its own undoing, because reflecting twice restores the original position. Thus the symmetries of the square form a group. This example contains much of the soul of group theory. The group is not primarily about numbers. It is about transformations. The operation is not addition or multiplication in the usual numerical sense. The operation is composition, meaning performing one transformation after another. Let us say that again slowly. In a symmetry group, the product of two symmetries means doing one symmetry and then doing the next. The product is another symmetry. The identity symmetry is doing nothing. The inverse symmetry is undoing what was done. This same idea applies to rotations of a regular polygon, reflections of geometric objects, permutations of labels, and many transformations in geometry and physics. Groups encode reversible actions. They do not merely list symmetries. They record how symmetries combine. This is crucial. The structure of a group is not just the collection of elements. It is the collection together with its operation. Two groups may have the same number of elements but behave differently because their operations combine elements in different ways. This is a recurring theme in abstract algebra. The operation matters. The structure is not only what elements are present but how they interact. Let us now consider subgroups. A subgroup is a smaller group living inside a larger group. More precisely, it is a subset of a group that is itself a group under the same operation. The phrase under the same operation is important. A subgroup does not invent a new way of combining elements. It inherits the operation from the larger group. It is a smaller world inside the bigger world, but it uses the same rule of combination. For example, among all symmetries of a square, we might look only at the rotations. The rotations alone form a subgroup. If you perform one rotation and then another, you get a rotation. The identity movement is a rotation by a full turn or by no visible movement. Every rotation can be undone by another rotation. So the rotations sit inside the full symmetry group as a subgroup. Subgroups help us understand groups by breaking them into smaller, more manageable pieces. When studying a complicated group, we often ask, what subgroups does it contain? What smaller structures are hidden inside it? How do these subgroups interact with the whole group? There is a useful conceptual test for recognizing subgroups. Instead of checking all group properties from the beginning, we can ask whether the subset is non-empty, whether it is closed under the group operation, and whether it contains inverses of its element. If these conditions hold inside an existing group, associativity is automatically inherited from the larger group. The identity also appears naturally once closure and inverses are properly present. The details can be formalized in several equivalent ways, but the intuition is simple. A subgroup must be stable under the operation and stable under undoing. If you combine two elements of the subgroup, you must stay in the subgroup. If you undo an element of the subgroup, you must stay in the subgroup. And the subgroup must not be empty. These requirements ensure that the smaller collection behaves like a complete little group of its own. Let us pause and repeat. A subgroup is not just any subset. It is a subset that is algebraically self-contained. It does not leak out when we combine element. It does not leak out when we take inverses. It contains the neutral behavior inherited from the whole group. It is a complete group inside a group. Now we come to generated subgroups. Generated subgroups express a beautiful idea. Sometimes a few elements, repeated and combined in all possible legal ways, produce a whole structure. Suppose we choose one or more elements of a group. We can combine them with each other. We can take their inverses. We can combine those results. We can keep going, always staying inside the larger group. The collection of all elements we can reach in this way is the subgroup generated by the chosen elements. It is the smallest subgroup containing those elements. This phrase is very important. The subgroup generated by some elements is the smallest algebraically complete world that contains them. If the chosen elements are like seeds, the generated subgroup is everything that grows from those seeds under the group operation and inverses. It contains exactly what must be included if we want a subgroup containing the chosen elements and nothing unnecessary. This idea is powerful because it shows how complexity can arise from simplicity. A large group may be generated by a small number of elements. In some cases, one element is enough. In other cases, two elements generate a surprisingly rich structure. In symmetry groups, a rotation and a reflection may generate all symmetries of a polygon. In permutation groups, a few simple swaps may generate many or all rearrangements. Generated subgroups are one of the first places where abstract algebra feels dynamic. We do not merely inspect a set. We build structure from elements. Now let us turn to cyclic groups. A cyclic group is a group generated by one element. This means that there is a single element such that, by repeatedly combining it with itself, and also using its inverse when needed, we can reach every element of the group. The word cyclic suggests repetition, and that is exactly the intuition. Begin with one action. Do it once, then again, and so on. Perhaps after some number of repetitions, you return to the identity. Then the pattern cycles. Or perhaps you never return, and the sequence continues indefinitely without repeating. Consider the rotations of a regular polygon. A single smallest rotation may generate all rotations. Repeating that rotation moves the polygon through all its rotational positions and eventually returns it to where it began. This is a finite cyclic group. Now consider the integers under addition. Starting from the number 1, repeated addition moves through the positive integers. Using the inverse direction moves through the negative integers. The identity is the number representing no movement. In this way, the entire infinite structure is generated by one element. This is an infinite cyclic group. The order of a group is the number of elements in the group when that number is finite. The order of an element is the number of times we must repeat that element before returning to the identity if this happens after finitely many repetitions. If it never happens, we say the element has infinite order. Let us say that more gently. The order of an element measures the length of its cycle. If repeating the element eventually brings us back to doing nothing, the order tells us how many repetitions are needed. If repeating it never brings us back, the element has no finite cycle. This idea is closely tied to symmetry. A rotation of a square by a quarter turn has a cycle of length 4. Do it once and the square turns. Do it twice and it is half turned. Do it 3 times and it is 3/4 turned. Do it 4 times and the square is back to its original position. The action has repeated and closed into a cycle. Cyclic groups are among the simplest groups, but they are extremely important. They are the basic models of repetition. They help us understand periodic behavior, modular arithmetic, rotations, and the structure of more complicated groups. It is worth repeating, cyclic groups are groups whose entire structure is produced by repeatedly applying one element. One element, repeated and then creates the whole group. Now we move to cosets and Lagrange's theorem. This is often one of the first genuinely new conceptual moments in group theory. It connects subgroups with counting. Suppose we have a group and a subgroup inside it. We can take an element of the larger group and use it to shift the subgroup. The result is called a coset. A coset is, intuitively, a translated copy of the subgroup inside the larger group. If the subgroup is a small pattern, a coset is that same pattern moved to another location in the group. The elements may no longer lie inside the subgroup itself, but the coset has the same size and the same internal shape as a shifted copy. The important fact is that cosets of a subgroup divide the whole group into non-overlapping pieces. Every element of the group belongs to exactly one such piece. Two cosets are either completely separate or exactly the same. They do not partly overlap. Let us pause and reflect on this slowly. A subgroup sits inside a group. When we shift it by elements of the group, we obtain cosets. These cosets cover the whole group. They do not overlap in a messy way. They partition the group into equal size blocks. This is a beautiful structural fact. Because each coset has the same number of elements as the subgroup, and because the cosets partition the group, the size of the subgroup must divide the size of the whole group, when the group is finite. This is Lagrange's theorem. In words, Lagrange's theorem says that in a finite group, the number of elements in any subgroup divides the number of elements in the whole group. This is a counting principle, but it is not merely arithmetic. It reflects structure. The subgroup creates equal-sized copies of itself throughout the group, and the whole group is assembled from these copies. Lagrange's theorem has many consequences. It tells us that possible subgroup sizes are restricted. It tells us that the order of an element must divide the order of the group, because the elements generated by that element form a cyclic subgroup. It gives us the first strong connection between group structure and divisibility. It is worth repeating the main idea. Cosets are shifted copies of a subgroup. These shifted copies divide the group into equal-sized pieces. Therefore, in a finite group, the size of a subgroup divides the size of the group. This is one of the first moments where group theory becomes a theory of hidden organization. A group may appear as a collection of elements, but its subgroups impose a rigid internal geometry. Now let us turn to homomorphisms and isomorphisms. A homomorphism is a map between groups that preserves the group operation. This means that if we combine two elements in the first group and then apply the map, we get the same result as if we first apply the map to each element and then combine their images in the second group. In plain language, a homomorphism respects the algebraic structure. It does not merely send elements somewhere. It sends them in a way that is compatible with the operation. This is a central idea in modern algebra. We do not only study objects. We study structure preserving maps between objects. A homomorphism lets us compare groups. It may simplify a group, represent it in another form, or reveal a hidden relationship between two algebraic systems. Two important pieces associated with a homomorphism are its kernel and its image. The image is the part of the target group that is actually reached by the map. Even if the target group is large, the homomorphism may only land in a smaller portion of it. The image records what outputs are possible. The kernel is the collection of elements in the original group that are sent to the identity element of the target group. In other words, the kernel records what the homomorphism collapses to doing nothing. This is a very important intuition. The image tells us what survives as visible structure in the target group. The kernel tells us what becomes invisible. If an element lies in the kernel, the homomorphism treats it like no action at all. The kernel measures the loss of information. A small kernel means little is collapsed. A large kernel means much of the original group is being identified with the identity. Homomorphisms are therefore tools for understanding structure through comparison. They show how one group can be represented inside another group, projected onto another group, or simplified by collapsing part of its structure. Now we come to isomorphisms. An isomorphism is a homomorphism that gives a perfect structural match between two groups. It is reversible as a map, and its inverse also preserves the group structure. When two groups are isomorphic, they may have different names for their elements, and they may arise from different contexts, but algebraically they are the same. This is one of the deepest ideas in abstract algebra. Abstract algebra studies structure, not notation. If two groups are isomorphic, then from the viewpoint of group theory, they have the same structure. The elements may be written differently. One group may be described using rotations, another using arithmetic, another using permutations. But if the operation behaves in the same way under a suitable correspondence, then the groups are essentially the same algebraic object. Let us pause and repeat that slowly. An isomorphism is a renaming that preserves all group behavior. It tells us that two groups are not merely similar. They are structurally identical. Anything true about one group in purely group-theoretic terms is true about the other. This returns us to the opening motivation. Abstract algebra is not mainly about what mathematical objects are made of. It is about how they behave under operations. A group of rotations and a group of arithmetic classes may look completely different, but if their operation tables have the same structure under relabeling, then group theory regards them as the same. This is why abstraction is powerful. It allows us to stop being distracted by surface appearance. A rotation might look geometric. A remainder class might look arithmetic. A permutation might look combinatorial. But the underlying group structure may be the same. Let us now slowly gather the ideas together. We began with the motivation of abstract algebra. The subject studies structure rather than isolated numbers. It asks how elements combine, how operations behave, and how mathematical systems relate to one another. Then we introduce binary operations. A binary operation is a rule for combining two elements. Algebra begins with such rules. It begins with the act of combination. We discuss closure, which says that combining elements keeps us inside the same world. We discussed associativity, which says that repeated combinations are stable with respect to grouping. We discussed identity elements, which represent doing nothing. We discuss inverse elements, which represent undoing. From these ideas, we built a hierarchy. A semigroup has an associative operation. A monoid has an associative operation and an identity element. A group has an associative operation, an identity element, and inverses for every element. This gradual building is important. Abstract algebra often grows by adding axioms one at a time and observing what new structure appears. Then we interpreted groups as the mathematics of symmetry. We saw that rotations, reflections, permutations, and transformations naturally form groups when they are reversible and composable. The group operation is performing one action after another. The identity is doing nothing. The inverse is undoing. This perspective gives life to the formal definition. A group is not merely a list of axioms. It is a language for reversible structure. We then considered subgroups. A subgroup is a smaller group inside a larger one, using the same operation. It is self-contained under combination and inverses. Subgroups reveal internal structure. Generated subgroups showed us how selected elements can grow into a complete subgroup. A generated subgroup is the smallest subgroup containing chosen elements. Simple elements, repeated and combined, can produce complex algebraic worlds. Cyclic groups are the most direct example of this. A cyclic group is generated by one element. Its structure is governed by repetition. Sometimes the repetition closes into a finite cycle. Sometimes it continues indefinitely. The order of an element measures the length of this repetition when it returns to the identity. Then we studied cosets and Lagrange's theorem. Cosets are shifted copies of a subgroup. They partition the group into equal size pieces. From this, Lagrange's theorem tells us that the size of a subgroup divides the size of the whole finite group. This is not only a counting statement. It is a statement about how subgroups organize the whole group. Finally, we introduced homomorphisms and isomorphisms. A homomorphism is a structure-preserving map. It respects the operation. Its image records what is reached. Its kernel records what is collapsed to the identity. An isomorphism is a perfect structural correspondence. It tells us that two groups are the same from the viewpoint of algebra, even if they appear different. Let us end by returning to the central theme. Abstract algebra is the study of structure created by operations. Groups are among the simplest and most important such structures. They capture the essence of symmetry, reversibility, and repeated action. They allow us to see common patterns across geometry, arithmetic, permutations, transformations, and many other mathematical settings. When learning group theory for the first time, it is natural for the definitions to feel abstract. But the abstraction is not empty. It is a compression of many examples into one language. Whenever you feel lost, return to the guiding picture. There is a collection of elements. There is a rule for combining two of them. The rule keeps us inside the collection. Repeated combination behaves consistently. There is a way to do nothing. There is a way to undo every action. And from these simple ideas, the theory of groups begins. Let us pause one last time and reflect. A group is a universe of reversible combinations. A subgroup is a smaller such universe inside a larger one. A generated subgroup is the universe forced into existence by chosen elements. A cyclic group is generated by one repeating element. Cosets are shifted copies of a subgroup. Lagrange's theorem says that these copies fit evenly inside a finite group. A homomorphism preserves structure. An isomorphism reveals that two structures are the same in essence. This is the foundation. Calm, precise, and powerful. Abstract algebra teaches us to recognize the same mathematical form behind different appearances. It teaches us that numbers, shapes, motions, and transformations can share common hidden grammar. And in group theory, that grammar is the grammar of operation, symmetry, and reversibility. So as the ideas settle, let the central message remain simple. Algebra begins with operations. Groups describe reversible operations. And symmetry, in its many forms, is one of the most natural homes of group theory.